Hello students, today we are going to start with the paper number 1, Semiconductor Devices and Basic Electronic Systems, having 2 credits and 36 lectures. So this year we'll be following choice-based credit system. Today we are starting with the chapter number 1, which is semiconductor diodes. In this, we are going to study semiconductor, P and N type of semiconductors, formation of PN junction diode, its working, forward and reverse bias characteristics, Zener diode, working principle, breakdown mechanism and characteristics, working principle of light emitting diode, photodiode, optocoupler, solar cell, its working principle and characteristics. So let us start with the introduction of the semiconductor. Basically, materials can be divided into 3 categories, namely conductors, semiconductors, and insulators. Conductors are the materials which can conduct electricity very easily through them. Example, gold, silver, aluminum, etc. Almost all metals, they are good conductors of electricity. Insulators are nothing but the kind of material which does not allow any electric current to flow through it, and therefore it is a bad conductor of electricity. Examples, wood, plastic, rubber, etc. Now, let us talk about semiconductors. As its name implies, semiconductor is a material whose conductivity lies in between that of conductors and insulators. That means they are working as conductors as well as insulators. So they are playing both the roles. Semiconductors are the devices which are perfect insulators at absolute 0-degree temperature, and they are working as conductors at room temperature. Examples of the semiconducting material are silicon, germanium, gallium arsenide, etc. Now, on the screen, you can observe 2 atoms. One atom corresponds to the atom of silicon. The atomic number of silicon is 14. So here you can observe the atomic structure and electronic configuration. So as atomic number is 14, there are 14 number of electrons in silicon, 2 in first orbit, 8 in second orbit, and remaining 4 in the last orbit. So the electrons present in the last orbit of silicon are 4 in number, and therefore the valency of silicon is 4. Similarly, if you observe atomic structure of germanium, you can see it has atomic number of 32, and therefore 32 electrons are present in germanium atom. As you can see, the first orbit can hold 2 electrons, second orbit can hold 8 electrons, third orbit can hold 18 electrons, and remaining 4 electrons are present in the last orbit. So again, you can observe that the last orbit contains 4 electrons. That means valency of germanium is 4. So in general, we can say that the valency of the semiconducting material is 4. And the materials with valency 4 are acting as semiconducting materials. Basically, there are 2 types of semiconductor. One is intrinsic semiconductor and another is extrinsic semiconductor. Intrinsic semiconductor are pure form of the material. there is no any impurity added to it. The conductivity of the intrinsic semiconductor increases with the temperature. So here you can observe how silicon atoms are arranged in the silicon material. So each atom is surrounded by 4 silicon atoms and they are bonded with a covalent bond. So here you can observe when your silicon is a perfect insulator, then it is sharing electron with neighboring 4 atoms, and all atoms, they are connected with the covalent bond. No free electrons are available in such a type of material at absolute zero temperature. So they are working as insulators at absolute zero temperature. In order to increase the conductivity of such type of material, you have to increase the temperature of the material. So when you increase the temperature of the material, then thermal energy will be provided to the electrons which are present in the valence band. And some of the valence electrons, they get this thermal energy, they become excited and they jump to the higher energy level, which is nothing but a conduction band, by leaving behind a vacancy, which is known as a hole. So when temperature of the intrinsic semiconductor is increased, electron hole pairs are formed. And these electron hole pairs are free charge carriers, and therefore the material, semiconducting material, is capable of conducting electricity through it at greater temperature. So number of charge carriers will increase with increase in the temperature. So conductivity goes on increasing with increase in the temperature of the intrinsic semiconductor. Now, let us move to the second type of semiconductor, which is known as extrinsic semiconductor. So in order to increase the conductivity of the semiconductor, a small amount of impurity, which is either trivalent or a pentavalent, is added to the semiconducting material. So when we add such an impurity to the semiconducting material, then its electric characteristic is modified. It can conduct electricity, or its conductivity can be increased. That is what we can say. So by adding external impurity to the semiconductor, we can increase the conductivity of the semiconductor. The process of adding impurity to the semiconductor is called as doping. There are two types of extrinsic semiconductor, namely P-type extrinsic semiconductor and N-type extrinsic semiconductor. If you observe the diagram which is present to our left, you can observe that the silicon material is doped with a pentavalent impurity, which is antimony. So antimony is trapped between the atoms of the silicon. It has valency of 5. What it does, it shares its 4 electrons with neighboring 4 silicon atoms, and 1 electron of antimony remains free. It cannot form any bond, and therefore it becomes free. So such a free charge carriers are available in extrinsic semiconductor, and the number of electrons which are present in such type of semiconductor are greater as compared to the number of holes which are present in the material, and therefore electrons are known to be majority charge carriers, and hence this type of material is called as N-type material. N indicates negative. That means majority charge carriers are electrons and electrons are negatively charged. Therefore, the material is called as N-type extrinsic semiconducting material. So in case of N-type extrinsic semiconducting material, the dopant material should be pentavalent. Example of the pentavalent impurity is antimony, phosphorus, etc. And the majority charge carriers are electrons, minority charge carriers are holes. Now, if you see the diagram which is present at the right hand side of the screen, then you can observe that the atom with trivalent impurity is added to the silicon lattice. Here, boron impurity is added to the silicon crystal. Now what happens? This boron forms, it has a valency of 3 and it can share its 3 electrons with the neighboring 3 atoms, and the 4th electron is not present in the boron, and therefore there remains a vacancy which is nothing but a hole. So in case of this type of extrinsic semiconductor, the majority charge carriers are hole and minority charge carriers are electron, and therefore this is called as P type of extrinsic semiconductor. P means positive and holes are positively charged and they are majority charge carriers. That is the reason. So thus, in order to increase the conductivity of the semiconducting material, they are doped either with P-type impurity or N-type impurity in order to form P-type or N-type semiconductor. Now, let us see what happens if the PN junction is formed. So P-type material is taken, N-type material is taken, and they are joined together. So the place where they are joined together is called as PN junction. The P-type material consists of holes as majority charge carriers. N region consists of electrons as majority charge carriers, and therefore the concentration gradient exists across the PN junction. The electron concentration is, free electron concentration is greater in the N region, while free electron concentration is smaller in the P region. And therefore, the process of diffusion takes place. And electrons from N region, they will move to P region. At the instant the junction is formed, the free electrons in N region near the PN junction, they begin to diffuse across the junction and they recombine with the holes which are near to the junction in the P region. So recombination of the charge carrier takes place. Now, if you see this diagram, you can observe that for every electron that diffuses across the junction and combines with the hole, a positive charge is left behind in the N region and a negative charge is created in the P region. So this static positive and negative charges near the junction, they form what is called as a barrier potential. The action of diffusion continues until this barrier potential repels the further diffusion. And at equilibrium condition, where such a barrier potential is developed, the further diffusion is stopped. So overall, in summation, what we can say, when the PN junction is formed, the electrons from N region diffuse to the P region, they recombine with the holes in the P region and form negative charges to the P side near junction and positive charges to the N side near junction. And thus, a depletion layer is formed at the junction. And this depletion layer offers a potential called as barrier potential because it stops the further diffusion of the electrons. This is what is happening when PN junction is formed. Now, as you can see over here, the barrier potential of the PN junction, it depends on the material that we are using. For example, at 25 degrees centigrade, the barrier potential is approximately 0.7 volt for silicon and 0.3 volt for germanium. And as the junction temperature increases, the barrier potential decreases because as the junction temperature increases, the charge carriers are increased and therefore the barrier potential decreases. So this barrier potential, it depends on the temperature. Now, as we have studied now, what happens when PN junction is formed. So such a PN junction is an electronic device and it is called as PN junction diode. When P-type material is joined with the N-type material, the PN junction diode is formed. The P-end is called as anode, while N-end is called as cathode. You can observe this is the symbol of the diode, and here you can observe this symbol signifies the arrow, and this arrow indicates the direction of the flow of current when your diode is in on condition. So the current flows from anode to cathode when diode is in on condition. So this is what is the significance of the symbol of the diode. Now, in order to use such a device in electronic circuitry, there is need to apply external DC power supply to it. There are two ways to apply DC power supply to the PN junction diode. One is called as forward bias of the diode, and second is called as the reverse bias of the diode. Now let us discuss about the forward bias connection. If you observe the screen, you can see that the external power supply V bias is connected to PN junction in such a manner that positive terminal of battery is connected to P side of the diode and negative terminal of the battery is connected to N side of the diode. This type of connection of PN junction diode is known as forward bias connection. Here you can see a single resistor is connected in series with this circuit in order to limit the current flowing through the diode. Now let us see how this type of connection works. When positive terminal is attached to the P side and negative terminal is attached to the N side, here we can observe that the majority charge carriers in the P region of the diode are holes and majority charge carriers in the N region of diode are electrons. And as P region is connected to the positive terminal of battery, you can observe that the holes which are present in P region, they are repelled by the battery terminal and they are pushed towards the junction. Similarly, as N region is connected to negative terminal of the battery, the electrons which are majority charge carriers in the N region, they are repelled by the negative terminal of battery and they are pushed towards the junction as well. So both holes and electrons are pushed towards the junction and they cross the junction and they complete the circuit so that current flows through the device. So forward bias is the condition that permits the current through the diode. So this is what is the case when during the forward bias. When external bias is greater than barrier potential VB, this condition should be satisfied. Then and then only the diode can conduct electricity in forward bias condition. Now let us discuss about reverse bias connection. Exactly opposite to that of forward bias connection, you can observe the PN junction connected in reverse bias condition. So here you can observe negative terminal of battery is connected to P side and positive terminal of the battery is connected to N side of the diode. Now let us see what happens here. So as negative terminal of the battery is connected to P side, the holes which are present in the P region, they will be attracted to the negative terminal because they are positively charged and therefore holes will move away from the junction. Similarly, if you observe N region is connected to the positive terminal of the battery and therefore majority charge carriers, electrons which are present in the N region being negatively charged, they are attracted towards the positive terminal of the battery and therefore electrons also move away from the junction. And what happens in reverse bias condition, majority charge carriers move away from the junction and they will not be able to constitute any current. So current flowing through the diode due to majority charge carriers in reverse bias condition is 0. And you can observe the width of the depletion layer is increased in reverse bias condition and the current flowing through the device is 0. But if we talk about the minority charge carriers, which are thermally generated charge carriers, electrons are present in the p region, holes are present in the n region, and these minority charge carriers, due to external battery, they are pushed towards the junction, they cross the junction and they constitute a very small amount of current in the device. So this current is called as a reverse saturation current. This is very, very small, almost 1,000 times smaller as compared to your forward current. So almost negligible current flows in reverse bias condition in case of PN junction diode. And this current flows due to minority charge carriers and therefore it increases with increase in the temperature. Now, let us go to next part of our study, which is nothing but current voltage characteristics of diode. Characteristic is nothing but a graph of current versus voltage. So here we are going to draw the graph of current versus voltage, both in forward bias as well as in reverse bias. Okay. Now, in a simplest way, if you visualize diode, its operation can be think of as a switch. When diode is forward bias, the diode acts as a closed switch or on switch, you can say. When it is reverse bias, it acts as open switch or off switch, you can say. Now, you can observe the diode characteristic. So, forward characteristic is present in first quadrant, whereas reverse characteristic is present in the third quadrant. So, forward characteristic is nothing but it is a graph of forward current versus forward voltage. Now, many things you can observe from this forward characteristics. Initially, the current flowing through the diode is very, very small and it suddenly increases when applied voltage exceeds the barrier potential and there is a steep increase in the forward current of the diode. So in this region, diode is going to act as an on switch. So this is a barrier potential, which is 0.3 volt for germanium and 0.7 for silicon. So when you apply external voltage slightly greater than this barrier potential, suddenly a large amount of current flows through the diode. So this particular voltage is also called as a knee voltage or cut-in voltage. So it is the voltage at which the current flowing through the diode suddenly increases in forward bias condition. Now you can find the resistance of the diode by drawing a slope to this graph. You can draw a slope to this graph. Here you can observe I am drawing a slope in a linear region of this graph. This is your change in current. Let us call it as delta IF. And this is change in the voltage, which is called as delta VF. So here we are going to define what is called as the dynamic forward resistance. It is a forward resistance of the diode, forward resistance. And this forward resistance is indicated by RF. And this RF is given by delta VF upon delta IF, which is 1 upon slope. Now, if you observe the reverse characteristic, which is present in the third quadrant, of the graph, you can observe it is a plot of reverse current versus reverse voltage. Okay. During reverse bias condition, generally a very small amount of current flows through the diode, which is called as reverse saturation current. This particular value is called as reverse saturation current. It remains almost constant until a certain voltage is reached, and this voltage is called as a breakdown voltage. If applied voltage exceeds the breakdown voltage, suddenly the current flowing through the diode increases and diode can damage. So diode is never operated in this breakdown region in reverse biased condition. It is always operated till this portion, till you get a constant reverse saturation current at a given temperature. Okay. So breakdown voltage is a voltage at which the reverse current through the diode suddenly increases, which will be responsible for damage of the diode or burning of the diode. So this is what is the diode characteristics, both forward bias and reverse bias. Three important parameters we get from these characteristics. One is the cut-in voltage, knee voltage or barrier potential. Second is the forward resistance of the diode. And third is the breakdown voltage of the diode. So here we are going to conclude our lecture, and next time we'll be learning the next part of the diode.